Right. Okay. Yeah. So you can see over here that we are having this HBr is required, and NABR is not required. Okay. Yeah. So HBr actually gives H plus, and H plus get attached to the lone pair. Okay. And the lone pair actually, you can see over here is the lone pair. Just a second. The lone pair get protonated. Okay. And it become OH2 plus. Right.
Yes, sir.
And the OH2 plus is a good, it is more polar now, it is more ready to come out, okay, as compared to the OH minus. OH minus was not ready because it was a strong base. Okay, that's what we discussed, right? So it was a strong base, so OH minus couldn't act as a leaving group, so that's why you need some H plus to make it get it protonated, and it becomes a good leaving group, and that is replaced by Br. And what is the role of ZnCl2? Yeah, tell me. So you can see HCl and ZnCl2 always written together. Whenever you want to take that OH out, it is because the ZnCl2 also has the same purpose. It is a Lewis acid catalyst, and it gets attached to the lone pair, and it helps to remove the OH. It is a Lewis acid catalyst. Okay. And the next question is, suppose if you have NABR, only NABR, will the reaction happen if you have only NABR?
No, sir.
No, correct. So what we did to make NABR HBr?
So we add H2SO4.
Yeah, H2SO4. So what H2SO4 will do? H2SO4 will give H plus, and that because some acids are not available in our lab. Okay, so we during the reaction we put something that will give HBr. Okay, and it will fulfill the purpose of HBr. So H2SO4 we took, and H2SO4 will protonate the NABR to HBr. Now it will have the reaction. Okay, that's what we expected. So you can see over here, these are the reactions. Similarly, yeah, HI, if you take the, you can simply, what you can do is you can select the OH and H. Okay, and remove them. Remove the water and put I in that, right? Clear?
Yes, sir.
Any doubt in the cyclohexanol secondary alcohol? Okay, this is which type of mechanism? This is SN1 mechanism, and this one is going to be the fastest. Why? Why it is going to be the fastest? Because the OH itself
The
is not.
carbocation will be more stable there.
Yeah, exactly. So OH itself is not going to come out. That's for sure, because it is a strong base. But in the presence of HBr, it got protonated to OH2 plus, and that OH2 plus came out as a water, leaving behind a carbocation. And remember what we discussed in SN1. SN1 is something substitution reaction where the good leaving group departs prior to the arrival of nucleophile, leaving behind a carbocation. And in this type of SN1 reaction can happen very quickly if your carbocation can form very readily, and it is a more branched carbocation, it will not have any problem in forming. Okay, right? Yeah. So what is the answer for this question? These two are NCERT questions, but very, very important. They are asked in JEE also. Okay. Yeah. What is the answer for first one? Why can NaCl not be prepared by reaction of phenol with HCl in the presence of ZnCl2? Either you can answer this one, or you can answer the structure which is written below it.
So because it has partial double bond character due to resonance.
Yeah. So OH actually has a lone pair, and the benzene also has a pi bond which is formed by sideways overlapping of the 6p orbitals. Okay, and those 6p orbitals are actually merged together to form a donut like ring. Okay, and that will help, that will let the electron, 6 electron, to move, okay, easily. But if you have OH, and the OH will also, that it has a lone pair, one of the lone pair will also overlap with these 6 set of p orbitals, and that will let the 6 electrons as well as the lone pair of the oxygen get into the ring. Okay, but this is a partial double bond character, so you can't remove such OH. Okay, so all these reactions with HX are not valid for aromatic alcohol. And what the answer for this one is? Yeah. What should I write at this position and this position? Yeah, Vamsi, tell me.
Sir, I think Cl will replace OH, which is attached to CH2.
Yeah, this is an aliphatic alcohol. Remember it. And it can come out very easily. Why? It can undergo SN1 very easily. Why? On the other hand, the OH on the left hand side can't come out. It's too reluctant to leave. It will not leave. Even if you take 10 moles of HCl or 6 moles of HCl or 20 moles of HCl or excess HCl. Because first of all, it has a positive charge, partial positive charge, because its lone pair is in the ring. Okay. It is in the ring, so it is not available for H plus to come and join in. Okay, but this cation can form very easily, because it will be stabilized by the benzene. Okay, and this CH2, sorry, and the Cl can come, and it is SN1, right?
Yes, sir.
And this question is also very, very famous. So just now we discussed, suppose if you want to make alkyl iodide out of alcohol, ROH, you need to take ROH plus HI. But HI actually you can't have it in your lab, because it get oxidized even with the air. So you can't have HI readily available in the lab. So you prepare it. You take a salt, right? Suppose if HI is given, then you will not say that is not available in the lab. Okay, then you will not say, you will just write the answer, whatever is forming, Ri plus H2, right? That's it. But if it is not given, then you need to prepare, you take some salt of iodide, which is Ki. Okay, clear?
Yes, sir.
And you need to take some acid. Which acid you will take? So this is a question, in-text question from NCERT only. But this is very, very important. That's why I have given here. So will you take H2SO4? And though it has already asked, H2SO4 is not taken. Why?
So because it is a good oxidizing.
Yeah, H2SO4, the sulfur is actually having +6 oxidation state, concentrated H2SO4, Muhammad. So you will get HI, but HI will get oxidized to I2. You will see some violet vapors coming out. Okay. Clear? But you want HI only. You want alcohol to react with HI. Mohammed, can you hear my voice?
Yes, sir.
Okay. So but HI is not available in the lab because it get oxidized by air, oxygen. So you need to prepare it. You took Ki, you took some acid so that the acid can give H plus to the Ki so that it can get converted to HI. But acid, the most common acid is H2SO4, HNO3. You don't take such acids which can oxidize. Okay, so which acid do you take? That's the question. Yeah. Mohammed Krishna, tell me quickly. Then which acid is preferred? It is H3PO4. Remember it. Clear? H3PO4 is used. Phosphoric acid is used instead of concentrated H2SO4 because phosphoric acid is not an oxidizing acid. It doesn't have tendency to oxidize. It will give only H plus. So you will get Ki, you will get only HI. It will not get oxidized to I2. Will you remember it? Very, very important.
Yes, sir.
Okay. Mohammed, understood?
So can you explain the previous questions?
Yeah, non-oxidizing. Actually, what happens is, suppose if you take, actually your purpose is to take HI. But if you take HI, so you took Ki, you took H2SO4. H2SO4 gave its H plus, so you got HI. But H2SO4 actually not only gave HI, it has some other purpose also. It is oxidizing acid. It can take away hydrogen. Oxidizing agent means the one who take away hydrogen. So it oxidizes, it forms
So it
HI and
can,
it oxidizes. It
it can reverse
oxidizes
the
HI.
reaction, right?
Yeah, it oxidizes the HI to I2. Yeah, it reverts, but reverts in some other direction. Right? So you got I2. So I2 is of no use for us because we wanted HI. So you need some acid that gives only H plus, but doesn't oxidize HI to I2. And you
So
need to
that's why we
remember.
use
Yeah.
H3PO4.
Yeah, H3PO4. Yeah, excellent, good. Yes, but you need to remember it because you can't use any other acid. Okay, H3PO4 is a non-oxidizing acid. You can write it. Okay.
Okay. So can you explain the previous question?
Yeah, this previous question is actually this will not come out because it will have a double bond character. Okay.
Okay.
And this isn't result. It will come again. Don't worry. Right. It is having a partial double bond character. So whatever that reactions which we are discussing, the conversion of OH to RI, okay, that is only for aliphatic alcohols. Okay, that is only for aliphatic. Aliphatic means the one which are connected to normal carbon group, not with the benzene, because if the OH is connected to benzene, that OH will the lone pair of that OH will interact with the benzene electron cloud and it will have some double bond character. It will not come out easily. So what product I made, I put OH here only. Okay, but I have removed the OH here, reacted, and this have not reacted. Okay, clear?
Okay.
Yeah. So yeah. Yeah. Next thing is this reaction. Next reaction is this one, right? Just a second. This is a very, very important reaction. Okay. This is a very, very important reaction. And this is the same reaction which we discussed. Okay. The same reaction which we discussed. Okay. Yeah, just a second. Some disturbance. Okay, just a second. Yeah. Mohammed Krishna.
Yes, sir.
Yeah, okay. So actually this is the next reaction. Okay. And this is the same reaction, but why I'm doing it again? This is known as Lupus reagent. Why? The HCl and ZnCl2 actually are removed to used for the removal of alcohol OH group. And why we take OH? Why we remove OH? Okay, how we remove? Because we took HCl, so H plus will give OH. H plus will protonate the OH. Okay. And
We will get water.
yeah, it will come out as a water. Yeah, exactly. So the purpose of this ZnCl2 will also have the same purpose, and HCl. So H plus is mandatory. That is very important. So actually you take ROH. Okay, it protonates and it's come out very easily. So this you get R plus and H2O. Okay, and the R plus will be
Cl
attached to Cl minus. Yeah. So this is a difficult step, the formation of R plus, because it is you're breaking a bond, you're forming an unstable intermediate, and this mechanism is SN1. Okay. So suppose if
So how
R plus
can we,
can,
so
yeah,
how can we identify that it is SN1?
SN1 is a reaction in which the leaving group is too good, means it comes out on its own before the arrival of nucleophile. That's what
Like
just
water.
yeah. And in this case it is water. Why it is too good leaving group? And just I was discussing with Krishna also that it is a very good leaving group because water is a neutral compound. It is very stable, right? That's why it
Yes.
can come out easily. Yeah, and the more branched alkyl group is, more easily it can form. Okay, because branched alkyl group can form a stable carbocation, because the carbocation will be surrounded by 3 alkyl groups and they will be give electron to the cation, and that will make that cation very stable and it can form very easily. And if it can, this is a slow step and it can form very easily. The next step, subsequent step, which is already a fast step, the attachment of Cl minus giving you the R, that can also happen very quickly. The main hurdle, the main difficult step is the separation of water and formation of cation. And if the cation is very stable, it can form very quickly, and the subsequent reaction will also automatically happen very easily. Okay, so this actually in tertiary alcohol it happens very quickly. It is a fastest, and in secondary alcohol, because we have only 2 alkyl group, it is less stable, so it is actually a bit slower. And primary alcohol is very slow, because primary carbocations have only 1 alkyl group, and if you have only 1 alkyl group, then you cannot make cation very stable. Okay, so but how you actually know that the reaction has happened quickly or reaction has happened slowly? What you observe actually with your eyes. Yeah.
So because of the stability of the carbocation, which decreases.
Yeah, this carbocation is very stable. Yeah. The speed of reaction also changes. This reaction with the tertiary alcohol, 3-degree alcohol, which in which the carbon is connected to 3 alkyl group, it happens very quickly. But how you notice that the reaction has happened, what you observe? That's what I want to ask. What is written over here? Yeah, Mohammed. What you notice, Pamsi?
So the product is formed immediately.
Yeah, product. Yeah, but how you know the product actually? Yeah, correct. Actually, alcohol is like water. It is soluble in water. Okay, and the alkyl chloride is insoluble in water. Okay, so when the product formed, the mixture become actually somewhat hazy, cloudy, or turbid. It loses its clarity. Okay, clear?
Yes.
Right. So if the reaction occur quickly, the alkyl chloride which is formed will appear quickly, and immediately the alcohol will get consumed. And alcohol is water like, it was clear, and immediately the reaction mass will become turbidity, haziness, or cloudiness. These three words are used, okay? And you note the time for the appearance of turbidity, haziness, or cloudiness. If the turbidity appears instantly, means it is tertiary alcohol. It can form a stable carbocation. That's why the reaction is happening very quickly. And the moment you put HCl and ZnCl2, immediately you get your turbidity. Is it clear, Mohammed?
Yes, sir.
Okay. And suppose if you put HCl and ZnCl2, and suppose if it is taking 5 to 10 minutes, means it is somewhat, the reaction is happening, but it is happening with some in between rate, means it is a secondary alcohol. But if you take primary alcohol, let's say this one, CH3, CH2OH, it will not break very easily. Why? Though the OH is same, H plus is same, but still the OH is not coming out. It is not the fault of the OH. It is the carbocation. The carbocation plus charge which is forming is just have one alkyl group on one side, means it can't get sufficient electron to become stable because plus needs electron. So for primary alcohol, no reaction at room temperature, or sometimes they say that they give turbidity after half an hour. Okay, clear? So actually this is the Lupus reagent. Let me summarize. Let me recollect all the things which we studied. This is a chemical reaction in which you convert alcohol to alkyl chloride by reacting with the HCl and ZnCl2. But this is also a chemical reaction which is used to identify the types of alcohols. And how you identify? You actually put HCl and ZnCl to the mixture which is known as Lupus reagent, and you note the time for the completion of reaction by noting the time for the appearance of turbidity or haziness. Okay, and if the turbidity appear instantly, means the reaction is very quick, means the alcohol is reacting very quickly and giving the alkyl halide, means the alcohol must be tertiary alcohol with 3 alkyl groups, because that 3 alkyl groups can form a stable carbocation. If you have a secondary alcohol in which the carbon connected to OH is connected to 2 alkyl group, then it will take some, and then it will react with some intermediate rate, means it is the rate is actually it is in between primary and tertiary. Okay, it will take 5 to 10 minutes to get that reaction completed, and you know how you appear that you look at the reaction mass. Okay, and if it is a primary alcohol, it will not react because it is a primary alcohol, or it react after 30 minutes, or it react very slowly, or it react only upon heating automatically on its own. It doesn't react because primary carbocation are not very stable. That is the reason. Okay, so if I give you 3 test tubes, okay, like this one, this is actually copper sulfate. Okay, if I give you 3 test tubes containing 3 different alcohol, but they will be colorless. One contain primary alcohol, another contains secondary, and another third one contain tertiary alcohol. And if you forgot to put label, can you tell me which test tube is having which alcohol? Tell me.
So if it is
What?
undergoing
So we
Lucas,
can see turbidity. We can check the turbidity, and then we can identify if it is tertiary or secondary.
Yeah, exactly. Okay. But sometimes primary alcohol can also give, this is for JEE. If someone asks you, sometimes primary alcohol can also give turbidity very quickly. It is because of the stable carbocation. Suppose if the carbocation is forming is like this, it can form very quickly. What is the reason why this primary carbocation is so special that it can form very easily? And I have written,
Double bond.
yeah, double bond. So this carbocation has MTP orbital. It is desperate to take electron, and on the neighboring carbon atom there is actually a source of pi electron cloud. and this can overlap and it can become stable. That's why. So on your own, you should not say until someone asks you.
Sir, I
Your
didn't
default,
understood the pi bond.
actually, it is a loose bond. There are double bond. It is a loose bond. So if there is a double bond, the electron density is above and below the single bond. So suppose if this is a single bond, the pi electron density is like this. The double bond, that is called double bond. Okay. So first bond is this one, pencil. The second bond has electron density above and below the first bond. Means it can be, it can help the cation to get stabilized. That is why. Right?
Yes, sir.
But this is only for some cases. You should not say this unless someone asks you. Your default answer should be this one. So Lucas test, Lucas reagent, it has two purposes. The first purpose is to convert alcohol to chloride, and the second purpose is to identify the alcohols. For primary alcohol, the time is maximum. Okay. Clear? Okay. So Mohammed, is it clear? Any doubt?
Yes, sir, no doubt.
Okay, very good. So now the next method is also, it is considered as a best method to prepare alkyl chlorides from alcohols using thionyl chloride. Thionyl chloride is SOCl2. Okay. And this is known as Darjan's halogenation. Why it is considered as a best method for the preparation of SOCl2?
Because the gases are escapable.
Yeah, because, and what is the trick?
So
Trick
OH
is,
leaves and Cl attacks the carbon.
yeah, actually this is the trick.
Okay.
So this is RCl, this is SO2, and this is HCl. And the byproducts are SO2 and HCl. They come out on their own and you get pure RCl. Okay, pure chloride. So you don't have to separate the byproducts. Is it clear? Why this is written? PY, what is this? This is pyridine. Actually, sometimes the HCl is absorbed by pyridine. This is a base and it reacts with HCl and it accepts the HCl. Sometimes it may be written. Even if it is not written, you must do the reaction. Clear? The best method. And what are the other method? Can you guys tell me? What are the other method which convert? What are the other reasons? Yeah.
Sir, from potassium chloride.
No, potassium. Yeah, I'm getting what you are trying to say, but you need to rectify it.
Phosphorus.
Yeah, phosphorus halides. Yeah.
Phosphorus.
So which phosphorus halides do you take? Yeah. Pamsi, you also tell me which phosphorus halides. Two types of phosphorus halides which you have. Yeah, Mohammed.
So like POCl2 and like,
Now, phosphorus halides. You have actually two types of phosphorus
Sir,
halides.
PCl3 and PBr3.
Yeah, PX3, right?
Yes, sir.
And PX5. Actually, they will be there in our P block also.
Sir, for PX5, there is only Cl as halogen, right?
Yeah.
Or we
Yeah.
can also use Br.
Yeah, X equal to Cl. Yeah. And for this one can be X equal to Cl or Br or I, right? So what is the trick? With px3, this is the trick. If it is px3, write px3 and write 3 alcohol molecules. Remove these. Clear?
Okay, sir.
Yes, sir.
This is a trick, but this is SN2 reaction. That also need to know if someone asks you what. And for PCl5, the trick is always same. Wherever you use PCl5, ROH. Okay. PCl5 had 2 Cl extra. Okay, so write it like this. The 2 Cl are extra. So write them like this. This is a short trick, not the mechanism. The mechanism is too long. So remove HCl, remove RCl and POCl3. That's how you can write the balanced equation. Is it clear? Okay, they are actually SN2 reactions, nucleophilic substitution. Okay. And sometimes PX3 can be prepared directly in the lab by taking red phosphorus and halogen. Halogen which we take are Br2 and I2. Why Cl2 is not written over here? For Cl2 you take directly PCl3. But if you want to prepare PCl3, you don't prepare it. Actually, you prepare only PBr3 and PI3. What is the reason? Because you can't add a gas to solid phosphorus. Br2 and I2 you can mix, but chlorine is a gas. So if you put chlorine into red phosphorus, it can escape and it is a very lethal gas. Okay, so you should not use red phosphorus plus chlorine, which is a gas, because it can come out easily and it is lethal gas. Okay, it can cause death also. So what you do, you don't take a risk. You directly use PCl3 as a whole compound. You react it with your alcohol. Okay, but in case of Br2 is a liquid, so you can pour the liquid. I2 is a solid, so you can mix it with the red phosphorus and alcohol and heat it. Automatically you will have PI3 formed. Okay, clear? So that's why it is written over here. Is it clear or not?
Yes, sir.
Okay, so look at these reactions. So this OH has been replaced by Br because you have taken PBr3. This OH has been replaced by Br. Okay, you need not have to write these stoichiometric coefficient. No need for balancing. Just write the product. And I told you this is SN2 reaction. SN2 means what? Inversion. So look here, I have shown you the inversion. The OH is actually coming up. It's a solid bond. Solid bond means it is coming out of the plane of the paper. And the PBr3, when it reacts with PBr3, one Br comes out and it attacks from the behind. So that's why you can see this Br. It is actually represented by dash. Which means that Br is getting into the plane of the paper. Is it clear? So this is SN2, right? Mohammed, is it clear or not? Any doubts? What about this one? Look here. This is which molecule? What is the name of this molecule? Very famous. All of us use it. Yeah, Vamsi.
So which one?
This one, the one which I have put on which I have put circle. Very common. This is actually glycerol or the glycerin, okay, which we use in our home. All of us must have seen glycerin. We have glycerin soaps also, okay. So if you react it with PCl5, it will have 3 OH groups, so all 3 will react. Okay. So PCl3, PCl5, PBr3 you can use. But very, very important thing is all of these reactions either with SOCl2 or with HX or with PX3 or with PX5 are not applicable for aromatic alcohols or phenols. What is the reason? Yeah.
So because it has a partial double bond character, which makes
Yeah.
it strong bond.
Yeah, the OH actually being adjacent to double bond, it gets into the ring, right? And it moves into the ring. This is the lone pair. It has shifted the pi bond. So in this, actually, we can see that the carbon-oxygen bond has gained double bond character. And if it has gained a double bond character, it means what? Means it can't come out. Is it clear?
Yes, sir.
Right? So I hope this is clear to everyone. Mohammed,
Yes, sir.
so if someone gives you this PCl3, what you will do? You will do nothing. Okay, don't react it. Okay. Now the next thing is nucleophilic substitution reaction on, till now we have seen nucleophilic substitution on aliphatic halides. Okay, alkyl halides, aliphatic halides. You replace CH3OH, right? And you have seen so many nucleophilic substitution reactions, okay, in which the OH was nucleophile, H2 was the nucleophile, RO minus, I minus was the nucleophile, NH3 was the nucleophile. Those nucleophile attack on RX. R was the aliphatic halide. Okay, aliphatic means methyl, ethyl. R is a general name for methyl, ethyl, propyl, butyl. Okay, but all of these reactions, and just now also I told you that these reactions are not valid for aromatic halides, right? What is the reason why they're not valid for? So just now we have seen, okay, this one, that this OH will not come out. Again, I have told you the same thing while discussing the reagent of phosphorus, that the OH connected to the benzene ring, directly to the benzene ring, will not come out. Okay, clear? That's what I told. Okay, so it is a, so then my question is, suppose if I want to replace a group connected to benzene, how do I need to replace? Suppose if you have, so let me recall what we discussed earlier. and all of you know it. Suppose if you have CH3Cl, and if I ask you to make it CH3OH, what you need to do? Yeah, Vamsi, tell me. Mohammed.
Reacted with water.
Yeah. But water is a neutral compound.
Or we can use sodium hydroxide.
You can use NaOH aqueous.
Yeah.
And it can happen very easily. Okay.
Okay.
But if you have done the same thing on chlorobenzene, aqueous NaOH, it will not come out. It will continue to remain as it is. Aqueous NaOH, at room temperature, no reaction. Why? Same answer. Yeah, Mohammed. What could be the reason?
Repeat the question again.
Now, why it will not react? Chlorobenzene, if you CH3Cl was displaced by aqueous NaOH. Why the chlorobenzene was not getting displaced?
Resonance.
Yeah, resonance, right? So let me write the resonance structure. There are two things actually.
Because of the resonance, it will be more stable.
Yeah, it is stabilized. Yeah. So why the chlorobenzene is less reactive and difficult to react with NaOH? So if you compare it with RCl, which is a normal aliphatic halide like methyl chloride, ethyl chloride, it will have a partial positive charge on the R and negative charge on the Cl because of the electronegative difference, and the R being partially positive, the carbon of the R will be attacked by the electron-rich species nucleophile, which is OH minus in this case, and the Cl minus will be forced to come out, and Cl minus can come out very easily because it is a good leaving group. Okay, in NaCl we observe that it is very stable. Okay, but in aromatic halides, the resonance happen, right? So resonance, you need to write this. These are ideal double bond. You can show them by writing. You can send these electron. These electron will get mixed up with the pi electrons of the benzene. Okay, that's what the resonance is. It is delocalization of loose electrons. Okay, but actually this is a carbon, so it will make only 4 bonds. So if the more electrons are coming from the Cl side, I need to push away one of the bond to push away the bonds of this extra bond aside in order to make the space for the incoming electrons. So this is the structure, resonance structure of the chlorobenzene molecule.
Sir, can you explain it again?
Yeah, actually this carbon is making how many bonds?
Sir, 4.
4. So if the lone pair electrons are coming and trying to form a bond with it, carbon cannot have more than 4 bonds.
Yeah, so
I
it
need,
will.
yeah,
pi bond.
I need to push this pi electron aside. I will put them here, and the Cl will have plus charge, right?
Yes, sir.
So it will again get shifted here. Vamsi, is it clear?
Yes, sir.
And it will again get shifted. And it will again get back to its original position. Okay. So actually the Cl is actually affecting the electron density of benzene in two ways. And what are those two ways? Yeah, tell me.
So can you repeat the question?
So this is one way. Okay, this is actually minus I effect, inductive effect. Actually, the sigma bond or the main bond between the carbon and chlorine which is there, it will have electron density like this. The Cl is minus and the carbon is plus. Okay. More electrons on the towards Cl side. Why? Actually, electron is not a particle, it is a cloud. So the cloud will be more towards the Cl. Because chlorine is more electronegative, it has a tendency to pull electron cloud toward bonded electron cloud toward itself. And that's why you have an partial negative charge, and this is known as, this you represent it in this way. And this is known as minus I, negative inductive effect of Cl. Right?
Yes, sir.
Is it clear? So this is one way, and this is the only way which was happening, which is responsible for creating charge on the alkyl halide. That's why the alkyl halides were reactive, because the carbon was having positive charge because of the inductive effect, minus I effect. The groups which pull electron are known as, yeah.
Sir, can you explain again from the inductive effect? I didn't understood from there.
Yeah, this is the electronegative atom. Non-metals are electronegative. Okay. So they have a tendency to accept electrons. So if you have Cl, and to whomsoever it is bonded, though it is a covalent bond, it will have tendency to pull electron towards itself. Right?
So that's inductive effect, right?
Yeah. This is because of the electronegativity of the Cl. And the group which pull electron towards itself, bonded electron towards itself, that is electronegative group, and the effect is known as inductive effect.
Okay, sir.
Okay, minus I effect. Right?
So due to this inductive effect, resonance is happening.
No, this is actually a different effect. Okay. This is responsible for creating a partial charge on chlorine and carbon. Right?
Okay, sir. So I guess that inductive effect is for haloalkane, not arenes.
Yeah, for haloarene it is different.
For haloarenes, is it resonance?
Yeah, for haloarene it is two-way it is happening. Two-way it is happening. Okay. So one is the inductive effect, which is there always because Cl is electronegative atom. But because the Cl has loose electrons and the benzene ring also has loose electron, and the lone pair of the Cl get into the benzene. So this is actually plus R effect. Resonance effect. Okay. Right? So actually, so I will say that this effect, the sigma electron are getting pulled toward the Cl, minus I effect, and the lone pair will get mixed up with the benzene ring. That is, okay, these are all the structures which are drawn here. So I'm putting just one arrow. This is the resonance effect by which the Cl is giving back electron to the ring. Okay, but there are two effects. One is this one, and another is this one. In halogens, because they are very electronegative, so minus I effect is more predominant than plus R. So one is trying to bring the charges in this direction, another is trying to bring the charges in opposite direction. Look at the tail of the arrow. This is indicating the plus charge. Okay, right? So because of that, the overall polarity of the carbon chlorine bond decreases and it becomes less reactive. Is it clear, Vamsi and Mohammed?
Yes, sir.
Yes.
So aryl halides, there is a two-way electron, like it is just like a train and a bus in a city. They move in different direction. They can, it is not that, there is no rule that if the bus is going in this direction, the train should also go, or the flight should also go in this direction. Okay, they have different movements. Okay, and if the Cl is pulling the sigma electron density towards itself, it is in this way, and the resonance movement is in another direction. Okay, so overall it actually decreases the polarity of the Cl bond in aromatic halides, or the Cl which is connected to benzene. So overall it becomes less reactive. This is one way. And by this resonance, the carbon chlorine bond acquire partial double bond character. And because of the partial double bond character, now we can't say that it will come out easily on its own, like it was happening in the case of water everywhere. Or in this case also, the Cl minus was a very good leaving group and it came out easily. But this is not the case. Though the Cl minus is good leaving group, but look at these structures, what has happened to the carbon chlorine bond by resonance. It has acquired a double bond character, due to which it is more tightly bound. The polarity has decreased. It has acquired a double bond character. It has more tightly bound. It can't come out easily. And one more thing, if you look at a benzene ring which is connected to Cl, the lone pair and the benzene ring electron density, okay, they actually, these orbitals, whatever these are there, they combine together, they join together, so that the electron of the Cl and the benzene ring can move in a more free way easily, and this create a electron density above and below the ring. And if suppose a nucleophile want to come and join to the benzene ring, like which we were doing in this case, now that nucleophile will be repelled away. Why? Because nucleophile sorry, is electron rich. The benzene ring is also electron rich. It has an electron density above and below the ring, because you have double bonds. Okay, the double bond is, the electron density will not be in the along the line joining the atom, it will be above and below. So the nucleophile will be repelled. Means what? Means if you take chlorobenzene, if you take cyclohexyl chlorocyclohexane, and if you take aqueous NaOH, okay, in this case the reaction happened easily. Okay, this is not an aromatic halide, this is aliphatic halide. Every cyclic ring is not benzene. Be careful. It doesn't have double bond. Okay, this is just like a normal alkyl halide. Okay, but if you take the same thing on chlorobenzene, which is aromatic halide, in which the Cl is directly connected to the benzene, you can look. Okay, and if you took any aqueous NaOH, just aqueous NaOH, OH minus dissolved in water at normal temperature, this is not going to react at all. because all of these reasons will prevent the reaction of OH minus and the benzene. So what you need to do? How can you make them react? Yeah. Vamsi and Mohammed, tell me. Any recommendation? How you can make them react? Yeah, you need to take temperature very high. Okay. So high temperature means more the OH minus Mohammed is moving with a very high speed. If it is moving with a very high speed, OH minus is moving with a very high speed, then it will have sufficient energy to get through this pi electron and give its electron to the carbon atom of the benzene. Is it clear? So you need to take high temperature, okay, and high pressure also. So look at the conditions here. 300 and 350. 350 degrees Celsius, 300 atmospheres. These are very, or sometimes it is written as that you take NaOH, molten NaOH. It will be very reactive. Simply by putting NaOH in water, normal NaOH will not make this reaction to happen. Okay, you need very strong condition, vigorous condition. Okay, so we are now talking about nucleophilic substitution reaction. Though we were talking about nucleophilic substitution right from the beginning of this chapter, but why I'm saying it again? Because now we are talking about the nucleophilic substitution reaction on aromatic halides. Till now we were discussing only for aliphatic halide, which was just a simple reaction SN1 or SN2. But now we are talking on aromatic halide. This is not a simple reaction. This has a different mechanism. The structure is different. Though to our eyes it may appear that it is just the same Cl. But I explained you just now that it is not the same Cl. You can see that so many things have changed. The way in which the Cl is bonded to the benzene ring has changed. So now the mechanism will also change. And what this mechanism is known as, in which you substitute the halogen from a benzene ring. This is nucleophilic substitution, but I need to get into the more detailed name specifically designed for this. Yeah. Mohammed and Krishna, tell me. Yeah. Any idea? This is known as bimolecular nucleophilic aromatic substitution. Bimolecular NAS. Nucleophilic aromatic substitution. NAS reaction. And it is bimolecular, just like SN2, but SN2 was happening on alkyl halide. On aryl halide, you will say bimolecular NAS. So how can it happen? What is the exact mechanism? Look here. What is the exact mechanism and why it is called bimolecular NAS and how it happens? First of all, you need to take very high temperature. First and the foremost thing is this one. Because you are not dealing with aliphatic halide, you are dealing with aromatic halide. Okay. So how it happens? So initially the OH, the lone pair of the Cl was involved in the resonance. Now the OH minus, which is taken at a sufficiently high temperature, will have sufficient amount of kinetic energy to come and join and donate its electron pair to the benzene ring. And because it is of sufficiently high energy, it will be able to push aside the pi electron cloud of the benzene ring. Is it clear, Mohammed? Vamsi?
Yes.
Yes, sir.
Okay, but you need very high temperature for this. This is not a normal reaction. And this is not SN1, SN2. In SN2, what happened? in SN2, the moment nucleophile started coming, the leaving group also started departing at the same time. But this can't happen because the leaving group can't depart simultaneously. And just now we have seen that it was connected via double bond connector. It was having a double bond. So it can't, that can't happen that one nucleophile come and leaving group goes. Okay, that can't happen. So first let the nucleophile come. Yeah.
So in brief, what can we say? Why do we need high temperature?
Because we need to overcome the less reactivity of the aryl halides. We need the OH minus to have sufficient amount of energy to react with the pi bond of the ring, which is a difficult task because benzene itself has a lot of electrons above and below, and the OH minus has electron. And you want two things which both possess electron to come together. Okay, they will repel each other. So you need to raise the temperature. Okay. So OH minus will come. Clear? It will push aside the double bond. Look here. I put a minus sign here. Okay. This was the same double bond which was there in between the ring. And temporarily this minus can, it is not sit at that position. It can move into the ring because it can push aside the electrons of the double bond, which is lying ahead of it in the ring. Look here how it is happening. So this minus charge which is generated by the attack of OH minus nucleophile will temporarily push aside one of the pi bond, and that pi bond will appear on the one of the carbon as minus charge, and that minus charge can push aside the further pi bonds of the ring, and the minus charge can, that's how, get at various places into the ring. Okay, and this is the hybrid. Okay, look at the way in which it is written. This is the way, because the minus is getting delocalized in this region. Okay, and the minus charge is written at the bottom in the middle. Is it clear? This is the actual average structure. Okay, is it clear? This is known as Meissenheimer complex of NAS. This is the complex which is formed in bimolecular NAS reaction. Okay, you notice a clear pattern in these reactions. Okay, you need first of all a very high temperature. Okay, but there is one more pattern. There is something which is making this reaction very easy. Can you notice it?
So addition of NO2.
Yeah, addition of NO2. And suppose if you have NO2 at 3 positions, Mohammed, which is the third case, if you have 3 NO2 groups, and those NO2 groups also you need to place at a specific position. This molecule can react simply with water just by warming. Just by a little bit of warming, it can get. The Cl will get displaced by the water, or you can take NaOH also. Just by a little bit of warming, it can react. It has 3 NO2, and this compound which you will get is known as picric acid. This is the common name which is very important. You need to remember the common name also. Clear? So the presence of NO2, this is one thing. So we have noticed two things. So this reaction, let me summarize quickly. This reaction is different from the substitution reaction which was happening on alkyl halide. This is the substitution reaction happening on aromatic halide, which is a very difficult task because the Cl is involved in resonance with the benzene ring, due to which the carbon chlorine bond has become less polar. It has acquired double bond character. Attack of nucleophile was difficult on the benzene ring. So you compensated it by taking high temperature to give OH minus sufficient amount of energy so that it can come and get into the double bond and push the electrons aside. But another thing which we notice here, the presence of NO2 groups at ortho and para position with respect to the Cl, with respect to the site where the attack is taking place, is making the attack more and more easier. And the temperature, you can notice that it is helping. Okay, the NO2 groups are helping the reaction to occur more easily. Okay, so why? That we can discuss. Now, another thing is, let me complete the reaction first and then we can discuss the role of NO2 in this making this reaction happen in an easier way. So this is how what we got, okay, by the attack of OH minus. Okay, is it clear? This is known as sigma complex or Meissner-Heimer complex. But remember guys, this is not going to stay in this manner only because it is still an intermediate. Okay, it is not a stable compound, so it can't continue in this way. Okay, this is just a temporary stage. It will get back to the benzene ring again because benzene is very stable because of its resonance. So this minus will again form a pi bond to complete the benzene ring. But this carbon, look here, look very carefully. If this minus charge wants to get back into the double bond, okay, here it need to push away, and this carbon is actually making 4 bond, one with Cl, one with OH. This is one. These already 4 bond. If this minus want to recreate the benzene again, this minus need to push aside any one of the group. So who will be removed? Is it the OH minus or the Cl minus?
Cl minus.
Yeah, the one who is stable, the one who can come out. So Cl is larger. It is more electronegative. It can pull it is a non-metal. It is a larger bond, so it is weaker. It can come out more easily as compared to OH minus. OH minus is a very strong base, we know. So Cl minus will come out. Okay, and you can see the product has formed. The OH will continue to stay at its position. And Cl minus actually came out as a liquid. So on aromatic substrate, the reaction has happened in a different way. And that way is neither SN1 nor it was SN2. It was in fact entirely a new way, which is known as additional elimination mechanism. Actually, the nucleophile came and joined itself to the benzene ring, creating an intermediate which was temporarily stabilized by resonance within the some part of the ring. And that minus which was formed again attained the benzene like structure by pushing away the Cl. So this is additional elimination mechanism, and this mechanism was not possible on normal alkyl halides because normal alkyl halides were having 4 bond, and you can't expect a nucleophile to come and sit without any one of the group leaving out of the structure. Is it clear?
Yes, sir.
Okay, so this is bimolecular NAS. The first step is difficult step because the nucleophile has to come and push aside, and the rate is, what is the rate law? Yeah, K times the concentration of it will depend upon the concentration of both of them. Is it clear?
Yes, sir.
Mohammed, is it clear? Because both species are involving into the reaction. So concentration of both of them will affect the rate of the reaction. Now we can talk about the NO2. Why NO2 is helping the reaction to happen more and more quickly. You can see as the number of NO2 group increases, the temperature decreases and the reaction will happening more easily. Why? What could be the reason? Yeah, Mohammed, any idea?
So can you repeat the question?
Why the presence of NO2 group is making the benzene ring more reactive towards nucleophilic aromatic substitution reaction? That's my question. Why the NO2 groups is making the reaction to happen in a more easier way? Why?
So it destabilizes the aromatic ring.
Mm, yeah, actually, this is a very general statement. You need to be very specific. Actually, NO2 also participate in resonance. There are two ways to understand this. Mohammed, are you getting? The Cl actually has a lone pair. It has ideal electrons. So Cl can give only its electron pair. So Cl, if it gives its electron pair, the ring will acquire minus charge at ortho and para positions. But if you have NO2, NO2 is like this. NO2 doesn't have any lone pair. In fact, it has a positive charge and double bonds between nitrogen and oxygen. So it can also participate in, it can also let its electrons mixed up into the benzene. But it is the other way around. The electron, unlike the case of Cl where the electron of the lone pair of the Cl were getting into the benzene ring, in this case, this can't happen because N is highly electron deficient. It was having a plus charge, so it was pulling the electron. And that's how it was attaining a plus charge. Okay. And this plus charge is not going to sit where it was originally created. It can move by pulling pi bonds which are ahead of it. The plus charge can come over here. It can come at this position. Now, can you think why the presence of NO2 at the ortho and para position is making the attack of OH minus easier? So you can make the resonance structure. This is plus,
So
this is plus.
NO2 is
Yeah,
causing the plus I inductive effect, which makes OH
yeah.
group.
This is known as the resonance effect minus I inductive effect. Yeah, that is also true. But this effect is known as the pulling of electron by resonance, and this effect is known as minus I effect, and that effect is known as minus R. So in both ways, actually Cl was pulling and giving its lone pair. But for NO2, this is not the case. NO2 is pulling in the sigma electron, the main single electron, and the pi electrons also. The double bonded electron also, the NO2 is pulling. Okay. And that due to which the ring is having a plus charge at ortho and para positions. Okay. Clear? And but we are not interested in plus charge at every position. We are interested only at this position. So what it will do? So it will make the attack of OH easier. And if there are two NO2 groups, this due to this NO2, you will have plus charge at this position, this, but you need to write the resonance structures. You need to have the resonance structure which we discussed earlier also. Okay, I think I showed you the resonance structure earlier. Look here, these are the resonance structure which I have shown you earlier. Okay, in the previous classes, look how it is happening. Okay. Okay, but little bit practice you can do, though this resonance structure will come again. So you don't have to worry at all, right? They will come again. So, but you need to concentrate, and you need to know, okay, because every time they will come, every time they will be used, okay, in the reactions. So if you make them perfect, that will be very good for you guys. Okay, you can answer all the questions very quickly. So this NO2 is also there, so this will also pull the electron, and there will be plus charge, one more plus charge, one more plus charge, due to 2 NO2. So look here, this carbon has acquired very strong positive charge. Now OH can attack very quickly. Okay, clear? Or you can see this also, the minus charge which has formed in the intermediate, that will form at ortho and para positions, that will pass through ortho and para, and once it pass through para position, it will get into the NO2 group also, so that it will get stabilized by the NO2 group. Is it clear? So that's how it will become more and more stable. So, or in general, if you don't get into the detail, if you want to just know the, if you just want to tell the in a superficial way, you can say that NO2 groups will make the electron ring more deficient, and that will make the attack of nucleophile easier. Is it clear, Krishna? Any doubts?
No, sir.
Okay, so let's do this reaction. Towards biomolecular NAS. Compare the reactivity of the following compound towards the biomolecular NAS reaction. Okay, the same reaction which we discussed just now. This is chlorobenzene. You can consider it as a reference, means it is the at the base level, and some of the rings are more reactive than this, and some of the rings are less reactive than this. Right? And this is a question which is asked in all the examination, in JEE, NEET, everywhere. You are preparing for mains or advanced? Yeah, Vamsi.
Sir, am I audible clearly?
Pardon?
So I'm saying whether I'm audible clearly.
Yeah. Earlier some breaking voice was breaking. Now it is clear. So you need to compare the reactivity of these rings towards the attack of OH minus, or general I am saying biomolecular rings. Decreasing order of reactivity. Yeah. Which one can react with NaOH most easily? So we discussed that E. Okay.
Yes, sir.
Yeah. E was the most
So
reactive.
EDC.
EDC. Yeah. And C and B. B is less reactive. Why?
So because NO2 is in the meta position in B.
Yes. So NO2 will pull the pi electron of the benzene, and this is known as minus resonance effect, negative resonance, yeah, or minus M effect, and that will bring a partial positive charge at the ortho and para position with respect to NO2. Okay. And for this NO2, the partial positive charge is coming at these positions. Okay. So first of all, it is not coming directly at the position where the Cl is connected and where the attack of OH minus is going to happen. So though this NO2 is creating a plus charge, it will make the ring more reactive because the ring is ultimately being attacked by the nucleophile, which will bring in electrons. So plus charge, creation of plus charge will help. But it will not be as good as in option C, where the plus charge is directly created at the carbon atom bearing the Cl. Okay. So C is more reactive than B. B is reactive as compared to A, it is reactive, but not as reactive as C. Is it clear? Okay. Yeah, Vamsi, am I audible? Yeah. Vamsi, am I audible now?
Sorry, sir, I got disconnected.
Yeah. So yeah, what is the final answer of this reactant? Yeah.
Sir, I will get displaced and there will be
Yeah.
OH.
I will get displaced, yeah, because I is actually activated with respect to NO2. Is it clear? Not the BR. So this will not be
Yes.
the answer. Okay. This is going to be the final answer. So you need to look at the group which is actually activated and how activated for nucleophilic aromatic substitution, and how you are going to make out. You need to look at the group which is exerting minus R effect resonance through resonance, and that's how it is bringing positive charge. And that will help you to decide which one will react, which one will not react. Okay.
Yes.
Yeah. Which one will get displaced?
Sir, Cl.
Yeah, it is the Cl which is more activated, because Cn will again pull the electrons, right? So next time we will start with elimination reactions. Okay. So this is NAS. Next time we will be starting with we will do some problem of NAS, and we will move on to the elimination reactions given by alkyl halides. Okay.
Sir, can you list the substance which can deactivate the ring, like NO2 and Cn minus?
It can activate actually NO2. Look here, there is a difference. If you need to look at the EAS, this ring is deactivated. Because it has pulled away the electron density outside, right?
Yes.
And it has pulled the electron density outside. So if the electrophile wants to come and join in, it becomes very difficult, and it is million times slowly. It reacts million times slowly than benzene. Okay. But if you are looking for the attack of nucleophile, then this ring will be considered as activated, because it has a plus charge, and nucleophile, plus charge is an invitation for nucleophile. This is for NAS, and this is for EAS, right? So don't get mixed up.
So, sir, activated and deactivated depends upon the reaction what we are doing.
Yeah. Actually, but by default, if someone asks you nitrobenzene, is it an activated ring or deactivated ring? you are going to give your answer as per ES because electrophilic aromatic substitution are more common. Nucleophilic attack of nucleophile because benzene itself has an electron cloud. So attack of nucleophile are not very common. So by default, you will give your answer as per electrophile attack for with respect to the attack of electrophile. But if someone asks you specifically for EAS and for NAS, you need to change your answer accordingly. So electron withdrawing groups like CN, like NO2, all have plus charge or some double bond, multiple bond, electronegative atom, SO3H, COH. They make the ring more reactive for NAS. They are minus R exciting group. They will create ring in the positive charge. Clear?
Yes, sir.
Okay, but electron donating groups will hamper NAS reactions because electron donating group will make the benzene ring more negative. And when the benzene ring is becoming more negative, then the reaction will not occur quickly. It will become more difficult. Okay.
Yes, sir.
Okay. So let's do some problem next turn on the next turn and with more question, and we will start